All right. A pleasure to welcome you all to the first meeting of BunG seminar for this is autumn 2023, and it's a pleasure to introduce our speaker, Justin Campbell, one of our very own co-organizers, who's going to give an overview of the quarter and of Beilinson-Drinfeld's work that we'll be covering. Okay. Thanks for the introduction. I guess I'll start with the sort of definition of the objects of interest. So, what is a Hecke Eigensheaves anyway? There's various directions that I can approach this from, and one way would be to try to motivate everything thinking of kind of corresponding objects in number theory. And I don't know, I guess maybe in this talk I'll try to take sort of a more geometric approach. So if you know the number theoretic story, you'll see the parallels, but it's not something that gets really emphasized. So the idea here is, we're trying to study this particular BG category, right? So it's the name of the seminar category of algebraic P modules and the moduli stack of G bundles. And here, I guess I should define my terms. Maybe I can back up just a moment. Since this is the very first talk of the quarter, everything right in. So I'll work over an algebraic will there's 0, and as well be complex numbers, but everything be algebraic. G is a productive group. X is going to be a projective curve. Okay, so it's kind of the usual setup. Same as previous quarters. I don't want a one hand continuation of the earlier seminar, but also be friendly. The best. So the idea here is that again, so we're considering category of D modules, algebraic D modules on the modular stack of G bundles. And again, there's some technical work that goes into defining this, and I think I need to kind of take this input. If it's not familiar, you can kind of pretend, right? Pretend BunG is a variety, pretend that I'm talking about a billion categories. The concept is still kind of deep, but it's some very interesting algebraic geometric object. And I'm considering this category of algebraic models as some kind of cheat, right? So we want to think about this similarly. How do we think about function spaces in functional analysis and harmonic analysis? Somehow one category to level up, and this should admit some kind of spectral decomposition. And spectral decomposition, well, usually that's with respect to some operators or something, right? So these are the Hecke operators, which I'll define shortly. So the idea is we have some big family of commuting operators of local origin on this category, and we're trying to do spectral decomposition. Okay, so let me just, without further ado, introduce the Hecke operators. Again, we'll kind of come from a geometric perspective here. So first, what is the answer end of a geometric? So let me just start with a fixed point of my curve. The little x is the k point of the curve. And script h, this will denote it's called the Hecke groupoid at x. And this is an overview talk, so I'll be a little bit loose. So it parameterizes triples, right, where PG and PG prime are G bundles on the formal disk, centered at the point x. So that's like the formal completion of the curve at the point x. So this is kind of the local form of the Hecke stack. And so I have a pair of G bundles on the formal disk X, and alpha is an identification of their restrictions to the function list. So they're identified over the function list. Okay, this thing has a natural groupoid structure. There's a kind of convolution or a composition operation here, right? Which is if I have two such pairs and kind of the middle guys are the same, then I can compose the isomorphisms. And so, as such, this groupoid acts on BunG. Let me try to explain how this works. And I think probably the best way to explain this is there's this result of Bode-Laszlo. Again, it's not familiar, just ignore it. It's very intuitive. It's basically just that I can construct G bundles on the global curve by gluing data in a very natural way, right? So the moduli stack of G bundles can be described as follows. So I can think of it as I can identify these objects with triples the following form. Let's call it beta to distinguish it from alpha over here. It's the kind of thing. So I have a G bundle on formal disk, and this is a fixed point little x, right? G bundle on the formal disk, a G bundle on the punctured curve, right? So with little x removed, and an identification, this is beta, over their common restriction to the punctured disk. So again, there's some technical work, right, to prove that this really works in algebraic geometry, but hopefully this is a completely intuitive technique, right? I have something on the formal disk, something on the curve with the point removed, and then an identification on the overlap, and that is the same thing as global geometry, right? Okay, so from this perspective, the Hecke action is sort of clear. So this action there, right? If I have an element of the Hecke stack, so yes,
that this is what your last law is non-alternative.
Yeah, you can think of it as some kind of, I mean, there's like sort of two issues. One is that I may want to consider points where test schemes are not a finite type or something, and that's what you mean by the non-invariant part. And there's also the, like, if you really think carefully about what a descent datum is, it's not exactly what you might hope it is. There's like a little bit of it's a technical nuance. So yeah, there is this result of Bode-Laszlo that means this sort of thing works very nicely. You're taking points value and assuming.
So, but whenever you say but whenever you say Bode-Laszlo, it just means like I can glue it as if there were two of them.
Yeah, exactly. Behind your descent. Absolutely. Yeah, you just kind of pretend you're in some analytic. Yeah. Okay, so this action then. Sorry, I realized I wrote the action slightly wrong here. Sorry, it's a groupoid action, right? So it's taking place actually over a base, and that base is sort of, if you like, G bundles on the formal disk. So it's like the kind of way that this type of action works, right? Is that I have two triples. Like so, and here, you know, the fact that the action is defined on this fiber product means that these two are the same G bundle, right? This projection. Okay, then it's in terms of the kind of Bode-Laszlo type descent data, the G bundle I get by acting is this guy. So again, it's just composing these morphisms. So you know, again, if you I don't know if this formula actually helps, I can parse, but it's just you're re-gluing this data, right? replacing, again, I have my G bundle on the global curve is like a G bundle on the disk, G bundle on the punctured curve, and an identification of the punctured disk, which is the overlap. And I'm kind of replacing the G bundle on the disk with another G bundle, right, which I can then I can identify still the result of the punctured disk by composing it. Okay, so there's this natural action. And in particular, I get a correspondence sorry, say it. Okay, so I'm yeah, sorry. So PG double prime is on the punctured curve, right? And all three of the other bundles are on the disk. Right, so I'm sort of contracting here, right, and replacing this PG prime with this PG. So this is again on the disk, and I just have to identify them on the punctured disk, right? So I compose these two isomorphisms.
Sorry, so that's what I think. That's what you mean by this overbound of
G bundle on the normal disk. Yeah,
Right,
yeah,
so
absolutely. Yeah. So my stack is like the purely local version. Like only this HG comma X only has to do with the formal disk. It doesn't know the global curve. So I'm using this Bode-Laszlo gluing, right? To kind of again, if I have another G bundle on the disk, which is identified over the punctured disk, I can replace this one, right, with that other G bundle. Again, assuming kind of the guys in the middle of the same, right? And I can kind of track. Okay. I'll explain this in a slightly different way, just to realize it's a little bit hard to parse formulas, but there's another way that to me is a little bit more illuminating. Let me come back to it and just say this action gives me correspondence like so. Okay, and this is how I define the action at the level of sheaves, right? So this gives me an action of D modules on the Hecke stack. Again, let me just be a little bit informal and believe that all of the sheaf theory works very smoothly, these kinds of things, and kind of base change and all that sort of stuff. And the way that this is defined, right, is the action morphism is given by pull push. So it's as always, when I have a groupoid acting space, I can have my sheaf theory. Okay, so there's a slightly different way of phrasing this, and I think this is very helpful when I put it the first time. So let me just try to explain it quickly. So I can also consider this guy the algebraic loop curve. So sorry, that's my prime capital L. And it's like, again, I'm being a little bit loose, but it's basically the mapping space of maps from the punctured disk into the image. Again, there's some annoyance here with this punctured disk sort of here in algebraic geometry, and I think it's completion, but more or less it is. And inside it, I have the group of arcs, the algebraic arc group. This one is literally the mapping space from the formal disk to G. Okay, so in these terms, this Hecke stack is literally just the coset space. Well, coset space. If you think about how coset spaces, classifying stacks, and so on work, it's logical, I think. Right, this is exactly what this points at this double coset space parameterized. And I can realize BunG as a coset space in these terms. So namely, consider the space BunG level comma X. The LUV stands for level. terminology, I think, comes from number theory. And this parameterizes pairs consisting of a G bundle on the global curve and I don't know what's called it, gamma, I guess. So again, PG here is a G bundle on the global curve, and gamma is just a trivialization over the disk. In particular, this thing maps to BunG, right, by just forgetting the trivialization. And this is a coarser for the R group. If you think about the way trivialization works, right? Like, can act by the R group, that's just automorphisms of the trivial G bundle on the disk. And when I mod out by that action, I exactly get this G bundles. Global level. Why is it called a level?
Yeah, where's the level?
The level is the trivialization. So it's what, I'm not enough of a number theorist to really. Yeah, full level structure, exactly. I could do in the nth order neighborhood, you would call it the level structure of order n, or structure of level n. Sure. Yeah, and again, you have to ask for real number theorists. Maybe I would probably stumble if I tried to explain relation, but that is what the terminology is. It's analogous to the full structure. Okay, and again, this is a coarser for this part. So BunG is like something modulo.
Sorry, but that's I'm so sorry.
No worries.
That's this BunG level. How far is that away from the high-class model?
I mean, very far. It's still very much an object of global nature. Yeah, this G bundle on the okay. So if BunG, you think of BunG as like G of the Adels mod G of the integral Adels mod G of the fraction field, and then here I'm not modding out by G of O in one place, right? Like the G of O course. Yeah. Okay, and then the interesting thing here is that this is a coarser for the R group, but in fact, kind of by this gluing stuff, the action of the R group on BunG with full level structure actually extends to an action of the entire loop group. Okay, so if I mod out by the action of the entire loop group, I get something like G bundles on the open group. Okay, and so then this Hecke action, you can think of it, it fits into this kind of general pattern, right, of like double coset spaces acting on, well, just like the following, right, so that this convolution diagram becomes the following. So the thing on the top is like L plus G, L G mod L plus G. Sorry. Okay, one-sided coset space times BunG, which remember was this coset space. Okay, and then modding out by the middle action, diagonal action of the R group. So you can identify the top thing in correspondence there with this gadget. And then this is the projection. Double coset space. And here, this is the multiplication act in the middle, right? So I'm acting kind of by the, if you like, the middle action, sort of anti-diagonal action here. Okay, so there's multiplication, right? And so the multiplication of sorry, I realized I shouldn't have sorry. Sorry, sorry, this is what I meant to write. Okay, so it's this one-sided quotient times BunG with the level structure modulo the middle action here. So I have the projection on the one hand, right? Projecting each of the factors. Okay, and then I have the multiplication coming from the action of the loop group on BunG with the level structure. Okay, so that maps me to BunG with the level structure. Again, I mod it out by the art group over here so that symmetry is left over. Okay, and I get BunG. Okay, so again, this is just some general pattern. Anytime I have a group, right, acting on some variety or scheme or whatever, right, and I have a subgroup, then the groupoid of double cosets acts on the quotient of the variety by that subgroup, right? Just kind of very, very general pattern. This kind of stuff. So that's a different way to think of it. Some general group theory. So I hope that was helpful.
This L plus G actually on function level is by modifying that as well.
Correct. By modifying the trivialization. Exactly.
But then how do you extend to LG? Doesn't that like screw up the order?
Yeah, let me try to say I'll probably get confused. So it's
You can't just compose.
no, it's like how do you say it? So think about this Localization type realization of BunG. So then BunG level is just going to be a G bundle on the function curve together with a trivialization on the function disk, right? Because once I choose a full level structure, PG is trivialized. So then I just act, the loop group acts there. So instead I have a trivialization on the punctured disk and the loop group acts there. Yeah, it's not something you can parse in real time. I feel the same way. Anyway, I think again, if you kind of let me just kind of as an aside say the general pattern here is like if I have G, let me say these if I have H acting on Y, right, I have some subgroup K inside of H, then the double cosets of K and H, the sets on groupoid structure, right? And this is going to act on Y on K by this kind of over point K. Sort of the space of objects. Well, actually, I mentioned this not just because it's a different perspective on this, but it'll be useful later for discussion.
How dependent on the choice of base points for X? Yes.
I'm going to discuss it. Yeah.
So there's like some competitive.
Yeah, I absolutely want to allow the point on the curve to move. I want to allow finite subsets of the curve and so on. But I'll discuss this in great detail. Question? Other questions? Awesome. That's page 1 out of 13. So let's go this goes.
One's always the hardest.
Yeah, very good. So okay, so then the first big kind of non-trivial input here, the first appearance of, in some sense, first appearance of Beilinson duality here is geometrics at Hecke. Okay, and it tells us that there is a canonical monoidal functor. So I have this category of D modules on the Hecke stack. It's some monoidal category, but it's kind of inscrutable. But in fact, it has relatively understandable structure combinatorially. Okay, and in particular, I have this monoidal functor called the geometric Hecke transform from representations of the Beilinson dual group. So the first time to check is during maybe in this seminar in general, into D modules of X. Okay, and I really want to take this black box, but well, I think the next talk is about so we'll be explaining down the road. very non-trivial, and again, there's some real kind of meat here in terms of the combinatorics, of like checking that the Lang's Holberg actually appears. They're beautiful. And again, I'm working in kind of the world of DG categories here, so this isn't actually an equivalence, but tensor product of G-check cards. That's the convolution on the next. So this induces equivalence. Unlike the situation with the billion categories, this DG category is not symmetric. But I get an equivalence on. Sorry? Yeah, representation is absolutely symmetric. Okay, so it's not an equivalence, but it does induce an equivalence on kind of perverse sheets on the heart of this structure. So this just means like not complexes of D modules or whatever, but actual modules, which are by Riemann-Hilbert are the same thing as perverse shapes. These really are just on the nose representation.
What about the policy? That's inside your discussion, but the right side is not. What I'm saying is going to give this.
Only on the heart. So the heart is in symmetric modal abelian category, but in the DG category, it's not symmetric. It's E3. Not E. So it's particular smart, but very interesting topic. Okay, so now I can come to some sort of provisional definition of eigensheaf. Before I can say what is an eigensheaf, it's like some categorical version of an eigenvector, right? But what is an eigenvalue? First question you should ask, right? So the Hecke eigenvalue in this context, I'll just say what it is and then I'll explain why this answer makes sense. So it's the G-check local system. I'll use simple like E. Okay, on the curve X. So by G-check local system, I mean local system in the Duran sense. Okay, there's a few different senses. You might understand this in some analytic sense as well, but here I'm really algebral and it's in the derived, sorry, in the Duran sense. So it's a G-check bundle with a flat connection. Okay, so like if G is GLN, G-check is also GLN. This is just a vector bundle with flat connection. Okay, why would this be a reasonable candidate for like an eigenvector? So in particular, for any fixed point of the curve, such a local system defines a symmetric modal functor like if I have some commutative algebra acting on a vector space, right? And I want to talk about eigenvalues, then I would probably say an eigenvalue is like a homomorphism from that algebra to scalars or something, right? So G-check is going to define a similar datum in this situation from rep G-check to vector spaces. And namely that sends a representation to, well, I have a representation, I have a G-check local system, and I have a point. Okay, so what can I pick up with that? Well, I can take the local system of vector spaces, right, attached to my G-check local system, and I can take its fiber at the lengths. Okay, that's an actual vector space. Right? Yeah, let me not emphasize it too much, but this. Okay, so again, this is sort of like, it's just the associated local system. So I have a G-check, I have a G-check representation and a G-check local system. I can do the associated bundle construction and get a local system. So I think it's good. then just take the standard representation. It's just a local system of vector space. Yeah. But in general, like this kind of not the impact. This is it's not a functor. So this is kind of like your homomorphism to scalars if you're thinking about the computer algebra acting on something.
Yeah. I have a vector function like this. I have a challenge representation. And then what like this representation, I think.
Well, first I have to take the associated GLN locus, like flat GLN bundle, right? So I take the bundle of trivializations, right? So that gives me a flat GLN bundle, and then I can kind of go backwards, right? So I sort of like went from the state like this local system, right, to a GLN flat GLN bundle, and then I can go back to a local system of vector space by doing the associated.
Okay, I think that's.
Sorry, I thought you fixed the GLN.
I think and then I also have a look at this.
Yeah.
The local system next to
Yeah.
and vice versa. But then you have to like
Okay, GLN local systems can be identified with local systems of vector spaces on the nose just by applying this construction to the standard representation. Here's what thing happens.
Sorry. So I see. So when you say, so
But if there's G-Tech is random, it's showing this there's no distinguish.
I think give me a like pure.
I get a local system. Yeah. Yeah. So this is kind of my like character. Character, check or whatever. I get one for each one. Okay, so here's like a very provisional definition of the Hecke Eigensheaves. For a couple of reasons. So again, it's with some fixed eigenvalue. Check, right? So of course it's some object with M in the object of the UChicago T modules and BunG. And what does it mean for it to be a Hecke Eigensheaves? Well, I wanted to kind of transform, right, in a particular way, right, with respect to the Hecke action. And again, very loosely, I can say it's equipped with isomorphisms. Following. So when I take a G-check representation V, applies Satake to it, right? I get a D module on the Hecke stack, and then I can act on him. Okay, and I want that to be identified with the vector space, right, that I wrote here. So that's the fiber of the associated local system of X tensored with M. So again, this is acting by this G-check representation on M produces just M tensored with the vector space. It's like when I, eigenvalue, if I act by an element of my algebra, I just get a scalar, right, times that vector. Namely, that element of the algebra applied with the character applied to it gives me a scalar. Okay, and so this is for any x little x and any G-check representation. And there's many things. There's several reasons why this is not completely satisfactory. So I'm just not going to write any words. We say, of course, you want this to be kind of functorial and be in an appropriate sense. These isomorphisms should be compatible, especially in the derived setting. That can be a bit hairy to say carefully. And lastly, and maybe most subtly, is we want this to kind of vary in X in a continuous way. And even more so, I could tell this whole story with some finite set of points of X, okay, acting simultaneously at several points. And we should be able to kind of do that in families as well. So that's sort of the next part of the story. Sorry? Yeah, absolutely. In particular, and I definitely want, this to vary in X in a way compatible with the connection and so on. Yeah. Right. Absolutely.
I have much more stupid questions than that's the deal. Like, why should I consider something like this to start with?
That's a great question. So, section 3 of this talk is called "What is actually going on?" So, I think hopefully my question will be interesting.
You're going to give some examples.
I mean, I think for you, hopefully, it's like, okay, it's but like,
Okay.
yeah, examples. Well, I mean, I'll sketch how you construct all of this. So, particular examples are maybe not so much easier than the general case.
Really, when you put the GM, that said something.
Yeah, absolutely. In fact, that's something that I meant to do in this talk, but I probably won't have time. Yeah, so for GM, okay, for GM, there's some Duran version of class field theory. So giving a flat line bundle on the curve is the same thing as giving a multiplicative flat line bundle on the card stack. Okay, and so that's for any local system, your Hecke eigensheaf would be precisely this flat line bundle. Yeah. Great. Other questions? Okay, so I think, because there's probably not going to be enough time to say everything I want to say, maybe I'll kind of emphasize the definitional questions of like what is a Hecke eigensheaf and so on, since we'll spend a lot of time talking about the construction of them later. So for this, I want to talk about the global Hecke action. And this is something that was not available to Beilinson-Drinfeld in the Richter book. Okay, and this is something it's very specific somehow to the Duran situation in some sense. And although I think there's been some progress in other settings, but like there's something very special here, which is that all G-check local systems on the global curve assemble into some kind of algebra geometric object. So this is all called LS, local systems. So this is the moduli stack of G-check local systems on X. Okay. And it's some kind of a slightly fancy algebra geometric object, unlike BunG. It's not smooth. In fact, it's actually not even an object with classical algebraic geometry. It's really derived. Now, if you make some assumptions, you can kind of ignore this. So, like, if there's sort of two reasons for it. One is if the curve has low genus, it'll be derived. Another is if the curve has if the group is not semi-simple. So if you kind of put yourself in the context that Beilinson-Drinfeld we're in, where it's like a semi-simple group and I'm working in genus of these two, then okay, it will be possible. So that's really what that has to do with. But in any case, I don't want to dwell too much on this point. You can just think about it. It's some kind of slightly singular, right, algebra geometric object. It is unlike BunG. So one sense in which it's better than BunG is it is actually quasi-compact, which BunG is very much not very interesting. But Loxus is quasi-compact. Right? So somehow, I said I wanted a spectral decomposition of D modules on BunG, and this is really the space that the spectral decomposition should occur over. Okay, so I said for any fixed G-check local system, I have this notion of Hecke eigensheaf. In fact, what I really want is for the whole category of D modules on BunG to in some sense kind of fiber over this object. Okay, so try to make some sense of this. Okay, so the first observation here is that if I fix a particular point in my curve, so this is kind of a redux of like the Hecke action in this spectral side. So for any fixed point of my curve, I get what you might call like the evaluation map. Okay, from local systems to the classifying stack of G-check. So namely, a G-check system, I can take its fiber, the point X, and this is just a G-check torsion. I have this evaluation. So now, if I restrict along this map, okay, I get a symmetric monoidal functor from quasi-coherent sheaves on point on G check, which is exactly representations of G check, right? To quasi-coherent sheaves on this set of local systems. Okay, so this is symmetric monoidal, it's restricted to quasi-coherent sheaves, right? So this symmetric monoidal with respect to tensor product. Okay. And idea here, again, I kind of want to have my Hecke property not just with respect to each individual point of the curve, but kind of globally. And so the Hecke actions at these separate points so again, just to be clear here. Remember, Satake at a fixed point gives me a monoidal functor from G-check representations to T models on the Hecke stack, which then acts on BunG. So I get this Hecke action over every check for every point of the curve, and I want to somehow integrate these over the curve, right? Package them all together.
Like that point on evaluation, is that sometimes forgetting the connections? That
It's just restricting to a single point. So like
I see.
yeah, the connection has nothing to do with it. This factors through BunG check.
I see.
So the Hecke actions should integrate to an action of quasi-co Localization check. In the sense that, for any particular point, if I do this evaluation, the local Hecke actions. Make sense? So this is what I would call like the global Hecke action. And maybe before I go into the actual construction of this, point out that this gives us then like a completely satisfactory definition of Hecke actions. Following reason. Suppose we had such an act. Suppose constructed this section for a moment. So if I fix a particular G-check local system, okay, this gives me a monoidal functor from quasi-coherent Localization check to just vector space, right? Namely, if I have a quasi-coherent sheet on Localization check, I can take its fiber at the point e.g. check, which is like a K point of the stack, right? You take its fiber. Okay, this is symmetric monoidal. Restriction along that from spec K into the stack. And so let me write vect sub e.g. check for vect with this particular module structure over quasi-coherent. But the usual thing, if I have a homomorphism from my community developer and scalars, I can think of that as a one-dimensional module over my algebra, right? This type of thing. So I'm just going to label that and say it has this particular action quasi-coherent check. Okay, so now here's the true definition. And it's really nice because I can even define like the PG category Hecke Eigensheaves on the notes. You category Hecke Eigensheaves with this prescribed eigenvalue. Going to be, well, I can say I can write two formulas for it. So one is, take. Yeah. Yeah. Right. So what's the mark? This definition.
Yes.
Again, I have a symmetric modal function. So my local system determines the symmetric modal functor from quasi-Localization check into vector spaces. So I can think of this as an action of quasi-Localization check on vector. That's a symmetric modal category. It's a module structure on vector. Just like if I had a commutative algebra and I had a homomorphism to scalars, I can think of that as a one-dimensional module over my commutative algebra, right? Okay, if I have a quasi-coherent sheet F and I have a vector space V, the action is restricts F to EG check. That gives me a vector space and then tensor.
Tensor
With the fiber of that representation of EG check. Yeah. Right.
So is there a like when I say number theory, I mean cluster field.
Yeah.
Is there a number theory analog with this?
Well, I mean, Locus is like a very decent thing. But
in what in all what you're saying, you have assumed percent actually is zero. That's
yeah, absolutely. Because I mean, again, I'm considering like my spectral parameters here. My Langlands parameters are G-check local systems with black connection. It's very much not what you want to consider in functions. I mean, that doesn't make sense there. So,
but up until
they're allowed local systems. Yeah. But I mean, no, like so like in function field world, Locus is like you can define it as an algebra geometric object at all, which I think there's probably a couple of candidates. Candidates is a restricted thing, whatever. So whatever it is, it's a stack over QL bar. And so you can tell this whole story, but just everything will be over QL bar. As well, she's on the sheet. Yeah. But here are things over. Okay, so Hecke Eigensheaves, right? These are supposed to be objects of the modules on BunG that transform, right, with respect to the action of quasi-Localization check, right, as this this particular local system. So I can think of it again. Just think about if I had commutative algebra acting on, that's a module over, right? And I have a one-dimensional representation of that commutative algebra. Say what an eigenvector is it would be a homomorphism from that one-dimensional representation to my module, right? So I can write a formula like this. In fact, I can write it also in terms of the tensor product. Everything is nice and kind of self-cool here. So, so I can also write this as a tensor product like so. This is like a tensor product of EG categories. In the world of code with the EG categories. Okay, and the point is, this formula is valid just because this metric nodal category is rigid. Like every compact object is realizable, and so I always have this kind of really nice self-validating situation with the HOMs. Same thing. Very fun. So this is the definition. And again, if you extract what is an object of this category in particular, okay, you'll get something like this. But this is, again, neatly packages everything. Again, it's just best, and I'm considering it as a module over quasi-Localization check. Yeah, that is enough character, right? That one.
Can you say again what that UChicago itself do?
As a module over quasi-Localization check. Yeah, so what is the statement? The statement is, if I have a rigid symmetric modal category and I have a module over it, right? So some DG category with an action of it, then the module is dualizable as a module if and only if it's dualizable as a DG category and the duals coincide. So for something like vect, which is obviously solvable, right? I just have normal duality on vector spaces. Vect and vect dual are the same thing, and moreover, they're even identified as modules. So again, if this is confusing, ignore it. You can just take this as the definition or this. Well, I'm just pointing out the things.
Actually, can us see how these changes keep them here.
Yeah, so in this form of it, right, you can evaluate. You can evaluate and generate it. Well, this is a copy of vect with a prescribed action of quasi-code, looks this. And so in particular, it has a distinguished the one-dimensional vector space, right? The generator here, I can evaluate. So again, it's if one categorical level down, right? If the algebra, lambda is a homomorphism. And M is the B module. Then this is what I would want to call a lambda is like check. This is what I would want to call the space of eigenvectors with respect to lambda.
So after passing this formation, this sheet of the G satisfied all the things.
Yeah, you can extract that. Again, if everything is derived, like you'll end up with some infinite tail of compatibilities or whatever, you should be able to write down these isomorphisms in particular at kind of the first level. Sure. Yeah. All right, so I have to apologize. Like I know it probably feels a bit fast. I'm just trying to kind of give a flavor of things. We're going to go into a lot of this stuff in much more detail. Okay, so just try to to the right, and please ask questions if something's unclear. But at the same time, everything is not totally familiar already. That's like the way
We can expect it and go.
well,
It's okay.
I'll try not to, but I reserve the right. Okay. So I think in the interest of time, actually, maybe I will skip the construction of the quasi-code looks at Kac action. One, because like it's just totally tangential for what happens later, and two, it's I'm stealing. We may not end up using them anyway. Like I think this is I wanted to make this point, like what is a Hecke eigensheaf really? And I think what I'm going to say after this, I don't really discuss the construction, but let me just say the idea really is like what I wrote over here. You somehow can integrate over the curve, or really more properly over all finite subsets of the curve, right? To go from all of these local Hecke actions and somehow integrate to this local Hecke action. Okay, so let me just say construction. Of the global Hecke action is due to data story. Something generalized vanishing theorem. So there's okay, so I promised to kind of try to go back to Dale. What I can do. So again, I think this will hopefully be helpful, but I'll also have to like say some words that I haven't defined and so on. So again, it's best you kind of follow along figuratively, if not literally. Remember, Localization deep check is not smooth, as I pointed out before. Okay, and therefore, in terms of sheaf theory, one ramification of this, so I can consider this variance of quasi-coherent sheaf, which is called incoherent sheaf. I think it did appear previously in the seminar at some point, so I'm allowed to use it, but again, I don't want to be unfriendly, so let me just say, you know, quasi-coherent sheaves on a nice stack like what says, it's a compactly generated category, and its compact generators are the perfect complexes, so bounded complexes of vector. IntCo, by contrast, is compactly generated by coherent complexes, right? Bounded complexes with finally generated homology sheaves. And there's always this comparison functor, which is like coherent sheaves included in quasi-coherent sheaves, and then I extend. There's a unique way to extend that that's compatible with colimits. And this functor is going to be an equivalence if and only if the stack in question is smooth, which it's not. So this is not an equivalence, which is to say coherent and perfect are not the same thing. Sorry?
What is this?
Yeah, so coherent sheaves include into quasi-coherent sheaves, and then there's a unique way to extend it.
What's the word? Like
Freely adjoin left on extension. So this is like some inductive system of coherent sheaves, just abstractly. Just realize them as quasi-coherent sheaves and literally take the colimit in quasi-coherent sheaves. Right? Okay, so it's some functor. One thing that is nice about Localization, I said it wasn't smooth, but it is what's called quasi-smooth. And what this means is that it's sort of a local complete intersection in a sort of derived sense. So whatever this means, let me just, if it means something, that's great. If it doesn't, ignore it. Okay, so it's like basically it's like a fiber product of smoothness, something like that, right? Even though it's not literally smooth, it's like one step away from being smooth. Okay, and that implies in particular that it is as a derived stack, it's eventually co-connective. Okay, this I think actually is not so hard to explain what it means. It's just what is in derived algebraic geometry, functions are not necessarily just ordinary commutative algebras, they're like DG algebras, right? They may have homologies in many degrees, but they can be in degrees 0, -1, -2, and so on. Homological.
I think they call this word.
Comics comes with scary name. So eventually co-connected just means like the cohomologies of the structure sheaf are bounded. They don't go off to minus infinity. Yeah, okay. So the structure sheaf is cohomologically bounded, is all this means. Okay, so again, I'm going to say the upshot of this. So if it's scary or whatever, just ignore it. So what this implies is that psi admits a left joint. In fact, it's fully faithful. Just to say psi is actually kind of a co-localization or whatever in the setting. It's like it's some kind of a Verdier quotient. And this functor is usually denoted by C. So this is something that's specific to the stacks that are eventually co-connective, but it's actually really easy to say what this is. So as I said, quasi-co is compactly generated by perfect complexes. Perfect complexes sit inside of coherent complexes, just index them. But perfect complexes sit inside of coherent complexes only in the eventually co-connective case, right? If my structure sheaf was cohomologically unbounded, then the structure sheaf itself would not be coherent because it would be unbounded. So this is really specific to the eventually co-connective case where the structure sheaf is cohomologically bound. Is that Makes sense? Okay. Yes, yeah, it's a, yes, absolutely, it's DG stack, not just, it's quasi compact, it's finite, yeah. Mhm. Yeah, so not just almost a finite type, but of finite type, which means almost a finite type plus eventually. Yeah. All right, and okay, and so what I'm trying to do here, I realize this seems like a digression. What I'm trying to do is actually formulate the geometric line length conjecture in the global situation. And you might kind of remember if you thought about this or like read about this stuff or seen talks about it, that there was this kind of first hope that D modules on BunG would be equivalent to this category of quasi-coherent sheaves on Localization. That would be kind of like the simplest possible world. Well, it turns out not to be the world we live in. So you might say, okay, well, this thing seems closely related. Maybe it's INSCO. Turns out to also not be true, but it's something in between. Okay, so there's this intermediate guy, which again, I'm not going to define because the definition really doesn't matter. It's just something intermediate here. Okay, so it sits inside of INSCO and it contains quasi-co. And it's singled out inside of all incoherent sheaves by some exotic sounding condition, which is nilpotent singular support. But again, detail is really not important for this purpose. It just matters that it's something that contains quasi-co properly and is properly contained in INSCO in general. And also relevant here is that quasi-co acts on INSCO. So this is going to be the spectral version of the global Hecke action. This comes from just the action of perfect complexes on coherent complexes, right? I can tensor a coherent complex by a perfect complex and it remains coherent, at least if everything is eventually co-connected. And then I can just kind of formally and extend and I get this kind of action. And this action preserves the nilpotent singular support. Okay, so yeah, not actually defining this guy, just saying it's something there, right? It's stable under the action of quasi-co looks set. And so now I can state the following theorem. I think this might be the first time it's ever been stated as a theorem and not a conjecture on the blackboard, because this amounts like days ago. Well, it's compatible with the global Hecke action. It's called global LG. So D modules on BunG is equivalent to incoherent sheaves with nilpotent singular support on those two. Wait, but the names there's redundant here completely. So it's pronounced. Thinking, Mario, Waldo, then Chen, Joaquin, version, and skate story, and Kevin Lynn, and Samuels. So the first of a series of several papers just posted on this website. Check it out. And it very much uses this Beilinson-Drinfeld.
Can't really BBC at all.
No, only maybe CFG. Okay, so actually, let me leave the definition of Hecke here, because the reason I'm stating this at all is just to emphasize, like, why should we expect that Hecke Eigensheaves exist? Should they be unique? Like, these are very good questions you might ask. And if you believe in this statement, then you can kind of see what's going on. So, before I can say it carefully, let me just say, first here, we should really distinguish between irreducible local systems and reducible local systems. So, if you check local system, it's called reducible if there exists a proper parabolic check and a p-check local system such that, you know, if it's induced from a proper parabolic, right? The reason for this is, like, you know, in the GLN situation, this would mean that the corresponding local system of vector spaces, like again, local system is reducible in the word sense, right? Okay. Otherwise, we call EG check irreducible. Okay, and then there's a piece of terminology on the automorphic side here. So the Hecke Eigensheaves is called Cuspidal. And I guess there are other ways you can define this, but this is kind of the spectral characterization. If its eigenvalue is reduced. Kind of an awkward way to state that, but I think you see what I mean. Right? So, Hecke Eigensheaves for an irreducible eigenvalue is called a Cuspidal Hecke Eigensheav. It doesn't come from a proper parabolic. The reason I bring this up is because this is very much related to the discrepancy between quasi-co and ins-co with local singular support here. So if I restrict myself to irreducible local systems, then that distinction disappears. So quasi-co on irreducible local systems maps perfectly to nilpotent singular support incoherent shapes. Okay, that's legible. Incoherent. So this discrepancy is only visible in the kind of locus of reducible local systems.
By the eigenvalue of the
well, the Hecke Eigensheav comes with some eigenvalue.
sorry.
It's an eigensheav with respect to some given eigenvalue, and I'm saying if the eigenvalue is irreducible, we call the eigensheav custom. Otherwise, it's custom.
I'm sorry, because of that does say irred at the top.
It does,
there.
yeah. Right, so
Well, yeah, that's not more fault. So.
annoying sticker there. Let me try to make that legible. And you should think, you know, morally, this is like saying locus is irreducible is much closer to being smooth than locus is. under those, basically the only reason it's not smooth is because of this derived stuff, and if, for example, if the, at least if the genus is large and G-check is adjoint, then, or semi-simple, then it's literally smooth. I think that's correct. But in any case, this, if I put this nilpotent singular support condition, these categories will coincide for general G.
So cis is smooth if G is semi-simple.
Locus irreducible locuses. Yeah, okay, yeah,
Gotcha.
And again, under like if G is semi-simple and G's curve is skewed, it's actually smooth. And so in that case, like quasi-co, these code alpha, these code all ones. You're saying if I put the nilpotent singular support condition, then these will actually coincide always. And so in particular, for an irreducible, you check irreducible. The kind of spectral Hecke Eigensheaves. So if I do this definition of Hecke Eigensheaves on the spectral side, it would look like this. Right? Okay. But again, if UChicago actually belongs to the irreducible locus, then these two become the same. And so this is really just so the corollary hopefully plausibly follows from the proposition. So what this is saying is that given geometric line lengths, Cuspidal, the expectation here is that Cuspidal Hecke Eigensheaves exist and are unique up to tensoring with the vector space, which is the best you could ever hope for, right? Just like an eigenvector is only unique up to scaling. There'll be kind of a more or less distinguished one, kind of gender.
In this statement, the corollary, you don't need to put L as local says G-check irreducible.
Because I assume UChicago was in the irreducible locus. So
It doesn't matter.
this will kind of factor through the irreducible locus.
But the left,
Think about defining it like one categorical look.
yeah, but the left hand side is your definition of category of.
Hecke Eigensheaves, but kind of on the spectrum. Yeah, exactly. So I'm saying given geometric line lengths, this would imply that Cuspidal Hecke Eigensheaves are just this are unique of this tensor vector space. So
They need to have strong one.
yeah, exactly. Yeah, it's a one strong.
How come it's not shooting?
Definitely not the right perspective. Sorry. Ask Sam Rex. So yeah, so like just to kind of illuminate here what's going on, the generator here, like again, there's some kind of distinguished generator here, the one-dimensional vector space on degree 0, that's going to correspond to kind of the skyscraper sheet at UChicago over here. So, and in INTCO world, like skyscraper sheet might be a little bit ambiguous because you could do kind of skyscraper in INTCO sense or quasi-co sense and side. But if we're in the irreducible locus and they do coincide, there's just a particular guide you would call the skyscraper sheet that you check, and that's going to be your spectral Hecke Eigensheet. So the Hecke Eigensheets are supposed to be the objects of D modules of BunG, the D modules on BunG that correspond to skyscraper sheets, at least for the custom.
In a irreducible case, like with the important single spot condition, this INTCO is still smaller than total.
Yeah. Wait, sorry. With the nilpotent singular support condition, yeah, this would be smaller than total. Yeah, and it's just because like it's kind of comes from the center. like, at least, okay, so let's say the genus curve is two, so I don't know about this. So it kind of comes from the center. It's like you have something there that looks like bundles over, sorry, it looks like locus in the center. So you have something that looks like of GChicago. Yeah, exactly. Which like locus of GM is not classical. It looks like a classical thing times like some derived scheme. So there's these derived directions that are going to mess you up, and that's kind of the only instruction. So if the group is semi-simple, that doesn't work. Okay, so that was my summary of what's actually going on. And let me just say, we're going to focus on the case of Cuspidal Hecke Eigensheaves in this seminar, and why? I mean, I don't know about you, but I'm always bothered when people are like, "Well, we couldn't do the general case. Let's just do this hypothesis. I'm not going to explain why it's significant." And so it's because you can actually you can reduce the general case. So for non-cuspidal, cuspidal Eigensheaves, we constructed cuspidal ones in geometric Eisenstein series. It's definitely completely understood. So you go and look at the papers of Brother and Gainsbury on geometric Eisenstein series, and each of them will have a section called Hecke property or something exactly proving this kind of statement. So, in other words, let's say, I am, for simplicity, let's say I'm not just induced from a proper parabolic, but I'm actually induced from a proper Levi. In other words, I'm a semi-simple reducible local system. So in that case, my irreducible local system for my Levi in check, right? If I kind of induct on the semi-simple rank, that'll correspond to some Cuspidal Hecke Eigensheaf for M, which I can then apply geometric Eisenstein series to. That's my Eigensheaf for the original local system. Of course, there's a base case here as well. So we can reduce to the Cuspidal case. It's kind of the usual yoga parabolic. We can reduce to the Cuspidal case by inducting on the semi-simple rank of G. There's also a base case, of course, semi-simple rank 0. That's when G is a torus. But that is also well understood. That's a form of possibility. The RAM version of possibility.
I was hoping to explain this it was done in this
maybe others. I don't know if it would fit into another one of the talks or something. It's somehow very orthogonal to the rest of this. Right? So we want to talk about the custom.
Yes, but I want to understand that.
Let's do it. Yeah, that's awesome. Yeah. You and I can. Okay. All right. Other questions about this? You picture stuff, and then I'll spend the last half hour just kind of briefly sketching the Beilinson-Drinfeld construction and what's going to happen. Seminar. So there's a few things we can kind of rephrase, and a few things we can make a bit more general than is done in that book. The spirit is very close. So the kind of star of the story of this construction is the notion of over. And I won't define it because it's a little bit involved, but that's definitely going to happen later in the seminar. So let me just kind of indicate a G-check over is a G-check local system in particular with some additional structure. I can say vaguely what it is. So together with a G-check reduction, not of the local system, but of the underlying G-check bundle, so that this reduction is not going to respect an connection. So I'll call it key G-check. Sorry, key B-check of the underlying G-check bundle. And there's also a condition. So that's data, and then there's a condition, which is that again the B-check bundle, B-check reduction is not supposed to be preserved by the connection, but it's kind of it sort of satisfies the transversality. Connection. So like in the case of GL2, right, like what is so I have a rank 2 local system on my curve, that would be my EG check, and a B check reduction of the underlying G check bundle would be a line subbundle, right, like a flag on my rank 2 vector bundle. The connection is not going to preserve that line. In fact, what it'll do is it'll map the line isomorphically to the quotient of the vector bundle boundary. So it exactly bumps up kind of one step in the filtration. Thing. So I won't say any more. It kind of is relevant for what I'm going to say, but it'll be defined in detail later.
Like it's never parallel to it.
Yeah, never preserved by the. Yeah, exactly. Very interesting and subtle definition, which I think came out of physics and figuring about it. So so let me just say, okay, so I have this moduli space with overs. And in fact, it factors through irreducible overs. I claim if a local system has a overstructure, it has to be irreducible. And even better, this is actually, well, I don't know, it's good in some ways, bad in others. It's not projective, which is kind of bad for reasons that will become clear, but it is a closed embedding, and it's even like a Lagrangian with respect to some kind of sequential structure, which I'm unable to comment further, but in particular, it has half the dimension. It's this type of thing. So it's not everything, but it's not too small either. Half the space of your reducible bundle system this way. Have an overstructure. So what Beilinson-Drinfeld did they constructed a Hecke Eigensheaves for each over. So for each irreducible local system with an overstructure.
I just asked for one thing.
Yes.
What does it mean to be reduction? A reduction of the line.
So I mean, I have a B check bundle whose induced G check bundle is identified with the underlying G check.
Okay, so you have a B check bundle. This is a pullback.
No. The associated G check bundle is identified with the G check bundle underlying. So in other words, like in for GLN, it's like it's a flag, but it's a flag that doesn't preserve not preserved by the connection. Right. Yeah. So Beilinson-Drinfeld constructed a Hecke Eigensheaves each G-check open. So again, you believe what I said up there, you know, if an open structure exists, it's unique, and there's sort of half-dimensional space inside of the reproducible ones. So this produces a bunch of Hecke eigensheaves over all of them. But as I'll now explain, so yeah,
you probably did mention before, but I didn't internalize.
Yeah.
You're saying that if this B production transversality exists, then it is unique.
yeah, that's right.
I would expect transversality to be like an open condition though, right? So it's maybe surprising, or maybe
It
it's.
is, but I mean, it's a priori, it's a groupoid, right? So,
Oh, I see. Okay, so you have some extra flexibility.
Yeah.
Okay.
Is this stack of overs?
Good question. So I think no, but again, it's pretty close in the same way that locus is irreducible is pretty close, and so in particular, it's probably well. Yeah, let me not say it. Incorrect. Yeah, I'm not sure.
It's a closed subset that is going to be positive.
All right. Yeah, it's probably plus. Like it's a fiber product of smooth things more or less. It's like a little complete intersection. Yeah. So yeah. So question. Why should this be possible? That's what the heck does the open structure do for you? One obvious question, and then a natural follow-up question is, can we do it something similar for an arbitrary irreducible function, right?
Or non-Borel parabolic.
Well, no. So the Oper structure is always persistent.
There's no notion of corresponding notion.
Yeah, it's a complete. Yeah, it's. I don't think it is. Okay, so I'll try to motivate this a bit in the last 25 minutes. Just again, kind of from a 2020 hindsight kind of perspective, like this kind of fits into a bigger picture nowadays. So I'll define a couple of related moduli spaces to Opers. So I can consider, local systems on the global curve, but I can also consider local systems on a disk or punctured disk or an open curve or all of these different kind of local things. So all of these kinds of gadgets will live over what's called the Ron space. So this is the moduli space of finite subsets, non-empty finite subsets of X. Very important object in the local theory. Can actually be written as a colimit over all finite non-empty sets. The powers of the curve. And here, the category I'm indexing over is finite non-empty sets with surjection. It does turn out to be actually a pre-sheaf and not a stack, so it's not homomorphisms or anything. And it's not a scheme or an in-scheme or anything. It's kind of infinite dimensional in the way that an in-scheme would be, but like it's a weird, like even if I just consider finite subsets of cardinality at most 3, that's already not. It looks like a weird blowdown. Okay, but it is some whatever. It's not so bad. So any kind of construction I was saying before, where it's like I can do constructions kind of point by point on the curve. Usually, you can also do them over finite subsets of the curve, and eventually just parameterized over the whole Ron space. It turned out to be a good way to do things. One really nice thing about the Ron space is it's actually homologically contracted. So it's global homology vanishes. Sorry, not vanishes. It's one dimension. Reduced homology. Okay, so I'm going to define a couple of kind of enhanced or upgraded versions of moduli space overs. So first, we're going to define, sorry, there's so many declarations. So the ramified global Ron. So what is this? It's first of all a point of Ron space. So I'll just typically write these as like an I tuple of points of X, keeping in mind that only, you know, I index them, but I really only care about the actual set that is their union or whatever. And I have a check bundle, a check local system, check bundle. Okay, so what is xi is a point of Ron space, or like write something x. EG check is a G check local system. I'll write parentheses x just to emphasize on the global curves. I'll be talking about this now. And EB check is going to be an overstructure. Remember, it's a B check reduction of the underlying G check bundle with some conditioning on not the entire over, but on x minus this finite set. So gamma xi here is the and it's just the union of this finite set, right? The graph. It's called unramified because the underlying G check local system is globally defined. It could, like, it has the EG check has no ramifications. I could do a version of this where EG check was also only rationally defined, but EG check is globally defined, and the overstructure is generically defined. But I keep track of the points. What runs.
Or is a priori only 5 over x minus points.
Sorry, say again?
I mean, this, when you, whatever the open before was, I thought it was like the EP check defined as a curve. But now we have.
But here it's only defined on open curve.
Hold on, this object, not an object, not an check.
Correct. It's a global G check local system with a rationally defined overstructure. Okay, and I can do a local version of this as well, where I work with like disks instead of global curve. So this guy will also live over Ron. So yeah, notice by the way, of course, this projects. Right, in particular, a finite subset was part of the data. Okay, so I'll call this similarly unramified local. So this parameterizes a finite set. So okay, the triple will look the same, such that can be different. So it's finite set. EG check now will be a local system on the disk, sort of multi-disk, right? So take the union of these points and formally complete it inside the curve. So you call it a multi-disk, right? And take the G check local system to be defined there. And then DB check is an overstructure on EG check restricted to the function. Okay, so very similar nature, but now just purely of a local nature. Global curve does not really appear here other than to kind of index the poles. Here's the moment. Okay. It's the like, okay, if x were a single point, it would just be the disk centered of x. If some x is some finite subset, it's like the disjoint union of those disks. But in general, like it'll be a parameterized set, and so you have to take like the union of the graphs and then form right? Multi-disk. Okay, so these are some, you know, again spaces of overs, but kind of the rational overstructure. And it fits into a correspondence. try to remember to put X here to indicate that it's the global ellipsis there. So I have a correspondence X, right? Because if I have one of these global unramified overs, remember UChicago was defined on the global curve, so I can project UChicago. If I have, on the other hand, if I have one of these things, I can restrict UChicago to the disk, right, and restrict the overstructure to the functions. So this Q here is just restriction from the curve, from the global curve to the disk, and from the function curve to the functions. Okay, so a conjecture which is like point conjecture, many cases are known. It's pretty close to being known. There's a little bit of subtlety here. Is that P is exergic. So it's expected that any UChicago local system admits a rationally defined structure. And I think I don't know if Beilinson-Drinfeld explicitly conjectured this. Mind at some point. And like I said, many special cases of this are known. In particular, maybe the one that's most relevant for us is the theorem of Orinikin, which says that if the center of G-check is connected, then the image of P contains the locus of irreducible. So in other words, at least if the center of the group is connected, any irreducible G-check local system admits a generic overstructure.
Significance of this conjecture is that every local system is upgraded to overstructure unless you're somewhere.
With some constraints. Expected and I rank it for something that's very close to, and again, we're mostly interested in these irreducible ones anyway, so G is SL2, or I guess G is PGL2 and G-check is SL2, a little bit of trouble.
So I guess the answer of this question is basically the answer of how they do it for everything.
Can you do it for?
To answer that question,
Yeah, exactly. For this purpose, you really just need to put rational overstructures in your systems. We'll be able to do kind of a version of the Beilinson-Drinfeld situation. So we know we can at least do it at the center of the dual group is connected. By the way, I think if you look at Orinikin's paper where he proves this, he doesn't include this hypothesis, and because he's using a slightly different notion of overstructure. I mean, I didn't even define it here, but like, if you define it very carefully, okay, which I think was even probably missed by Beilinson-Drinfeld in the original book, there's some subtlety here having to do with the center. And as far as I know, this was first noticed by Sam Raskin earlier this year. The definition they use is slightly incorrect, and it coincides more or less at the center of the dual group is connected. But in general, you'll be able to construct an overstructure, a rational overstructure in the sense of Beilinson-Drinfeld, regardless, and if the center is connected, this upgrades to sort of the true overstructure. But again, the center is disconnected, it's open. I don't know if you can do this by somehow modifying Orinikin's method or what. Just a note of caution. It's very large.
Oh, yeah, there's three light umbrellas there.
Perfect. Great. Okay.
So does it mean that on the Cuspidal level, the work of Drinfeld and
Yeah, I mean, given this conjecture, what I'm about to explain, yeah, I mean, as I said, the proof. I mean, I think in the proof they don't use this conjecture. I think they somehow skirt it, but yeah, it would. If you knew this, then by what I'm about to explain, you would be able to construct all Cuspidal like that. And in any case, you can do it with the center of the loops. Sorry. Yeah, I don't know, I like SL one too. I guess, well, I guess G equals P joke. Okay. Let's see, I've got a little bit of time left, and I want to sketch the construction. Just again, kind of from a bird's eye view level, we'll do much more detail later. So the other ingredient that I haven't discussed yet is Kac-Moody representations. So representations of Kac-Moody algebra, the other main thing up here. So again, I'm just going to like really quickly go over this, and it will probably be a little hard to follow if you haven't seen Cac-Moody algebras, but I'll try to make it kind of black box as much as possible. So there's this Lie algebra called the Kac-Moody Lie algebra, and if I fix a point in my curve, okay, there's this Kac-Moody Lie algebra. Yeah, let me say it in coordinate way, just so it's less confusing. So there's really kind of a family of such, and we're going to be interested in the particular one, which is the so-called critical level. Okay, so it's an extension of I guess I could just write this economically, this Laurent series of coefficients of G. Okay, so this is a Lie algebra. Like it's kind of by tensor Lie algebra with a commutative algebra. And this is going to be a central extension, so this is like a one-dimensional central extension here. And remember, any central extension of the algebras is determined by a two cocycle. Okay, so
here's dummy variable.
Yeah, see, it's dummy variable. I don't even know why I included. Yeah, okay, I'll leave it in case you refer to it. So it's a central extension determined by the two cocycles defined as follows. So the two cocycle will be a map like this, right? And it looks as follows. So I can write an arbitrary. This guy is spanned by things of the form an element of the Lie algebra tensor Laurent polynomial. Sorry, Laurent series, excuse me. So I'll define it on tensors, pure tensors like such. And it's given by the following formula: -1/2 times filling form, which I'll write as like kappa filling. Okay, so the filling form applied to x comma y times the residue of f dg. So this is going to be f. So dg is like a, if you like, it's kind of like a one form unpunctured disk, right? It looks like a Laurent series times dt. So f dg also has this form. And I can take its residue, which is the coefficient of t to the minus. Okay. And this defines this is scalar. Okay, so this is the so-called Kac-Moody cocycle. And it's a particular one. I can actually do this really with the killing form replaced by any kind of invariant bilinear form, but symmetric bilinear form, but this is the particular one which is called the killing, or sorry, critical level, excuse me. -1/2 times.
You chose another one, you just change by scale, that could be different.
Yeah. Well, I mean, it would give you a cocycle that's not homogeneous. It really does change it. Okay, so that's why I put kappa crit. Otherwise, I could put like any invariant form here. And what we're interested in this particular one. So
Yes.
Well, I mean, I think I can allow it. I think it can be arbitrary. It just won't be non-degenerate. I don't think I need it to be non-degenerate. I mean, I'll still get a cocycle. Just be. Yeah. I think it's still okay. Okay, and I can consider representations. Okay, so it's going to be the DG category of smooth representations of this. Sorry, this is the algebra. And what does smooth here mean? Smooth means like, you know, for any, okay, I'll only say it for, I said DG category, but I'm only going to say this for objects that are kind of genuine modules and not complexes, because just the define this as a DG category is actually really complicated. So let me just totally black box it and say, at least if we're in the abelian category world, right, and I have a genuine representation, what does it mean to be smooth? Well, it's just like what it does in chaotic representation, right? So if I have a module, and I have a vector in that module, right, there exists some kind of sufficiently large integer n such that if you're divisible by a large power of n, right, you fill that. Smooth enough. I mean, this is a topological deal, so you don't want to consider just abstract representation, right? You want to be compatible with this model. And also, we also require that C, again, you have to refer to it, any variable in the center, right, act by the end. And this is, by the way, I think relevant to your question, right? Because if I choose a different level, yeah, I rescale. Maybe the Lie algebras would be abstractly isomorphic, but I would get a different category of representation because of this condition. C is the center, so it's sorry, C generates this line, right? That's a, so like, yeah, this is the no, it's think about what an action. So like if G were abelian, say it was one-dimensional abelian, then this would be an abelian Lie algebra on the series. So in particular, the algebra structure would appear secret. He doesn't have to act correctly. It's a very interesting Lie algebra. I mean, again, I think hopefully there'll be lengthy discussion of it later because I'll talk about it and here first. But these things come up in all kinds of contexts for different reasons. Let me just say here, morally, you know, like the series is kind of like the Lie algebra of this loop group in G, right? So it's really carrying this fact of life that this has a very important central extension that you can consider. Okay, and so for any x, I can consider kind of a coordinate-free version of this. So where I replace, instead of doing power series in a variable, but the limit series, I use like the completed local name. It's fraction field at that point, and there's some coordinate-free version, so I can do this at any particular point of the curve without choosing a distinguished coordinate. But you have to think very carefully about how to do this, like when possible. And in particular, I can do this over bond space. Okay, and I get a version of this category. It lives over bonds. So like, yeah, so let me just say I can do it. There's a version of it at each point of the curve, and there's also a version of it that lives over bonds. So it's really what you call a factorization pattern. Lives over bond space, and if I take the fiber at some set of disjoint points they look like the tensor product. Okay, I'm very short on time. Say a few more words. So talk 6 or 7. Explain how there's a canonically defined localization functor.
Don't need to worry about the room reservation. We have reserved until infinity.
Awesome. Okay. There's a canonically defined localization functor called loc. Okay, well, there's a version of each point. There's a version of the Ron space. Let me just go ahead and do it all at once with the Ron space. The D modules. So here I'm sweeping something under the rug, which is that this should be a category of twisted D modules. However, that twist, they're twisted by some line bundle, and it turns out you can just identify it with the category of twisted D modules. So completely sweep this under the rug in each time. Just ignore what I just. So I get this this localization functor, and like, where does this come from? Well, it comes from the same kind of like Hecke patterns I was talking about earlier. So like the loop group of D, right, at some point acts on BunG with full level structure. At that point, okay, and that exactly gives us this localization. Sorry, I missed one thing. Sorry. This is not the full category of Kac-Moody representations, but those that are integrable for the arc. So, in other words, they're Lie algebra representations, but when I restrict them to like G double brackets T, they actually integrate to a representation. So this means integrable. Yeah. The smoothness might be kind of followed. Really, I mean, like, think about it just for like the degree 0 part, right? Like, for the, in particular, your copy of G acts T to the 0, like acts standard, which is not in condition, right? Yeah. Okay, so this gives me this localization functor. Let me just kind of say what the general pattern is. If I have some H acting on some space Y, then and I have some subgroup K inside of H, very generally, I'm going to get localization functor representations of the Lie algebra of H, which are integrable for the subgroup K to D modules on Y mod K. So some general pattern here this fits into. This will be explained in detail later. Of course, I'm ignoring the twist here. There's also a twist, but this is kind of the general shape of it. So it really comes from this action, right? If you kind of pattern match here. All right, almost done. All right, so let's bring the story of Opers and the story of Kac-Moody representations together. There's a theorem-ish, it's been published, but I think it's in the air. You don't write it down at this point. It's a mouthful. So there's a canonical representation categories. So it just means like overrun and kind of compatible with like the points colliding and so on. Called the fundamental local equivalence, critical level. It relates representations of Kac-Moody with the algebra at critical level, which are L plus G integrable. These are equivalent to quasi-coherent sheaves on that space I introduced earlier of unramified local orders. So this is some uber fancy version of the Fagan-Frankel isomorphism. Again, it's going to be the subject that we'll talk later. So as a consequence of this, you get that like functions on this space kind of act by endomorphisms on any object of this category, right? That's the kind of thing that they did it in sort of a they proved something that's basically. Okay, and moreover, this is actually Repchi-Check equivariant. So again, in the interest of time, I'm just going to be a little vague here and say, so first of all, Repchi-Check acts on the right-hand side. Namely, this space, remember, one of these point of this guy, right, was in particular a G-Check local system on the disk. So it projects the G-Check local system on the disk. Therefore, quasi-coherent sheaves on locus G-Check of the disk acts here. That's really just Repchi-Check. It kind of fibered over runs this. So there's some very natural action of Repchi-Check on the right-hand side. On the other hand, there's sort of a Ron version, right, of geometric stocking. Okay, and this Hecke category acts here sort of by virtue of this category Kac-Moody representations has an action of the loop group, which is sort of come from the adjoint action. Okay, the loop group on the algebra. And because I'm taking L plus G integrable representations, the Hecke category function. Okay. So again, hopefully this makes sense just on a purely pattern matching level and more detail later. Yeah, I'll explain something that's kind of it's going to be kind of the upshot of what to say. I don't really know like how to say what a global version of this category is, but I'll be able to say something.
You're still in the process of describing how to go from offer to eigen.
Yeah, absolutely. So what I've now explained is, according to this theorem, one of these unramified local G-Check overs corresponds to a Kac-Moody representation.
From that, you have to go.
And now I'm going to explain. So you can kind of imagine how it would go now, right? Because I can localize from here to get models on BunG. Then the question is, why would I get a Hecke Eigensheaves? So there's one more ingredient. Okay, so let me explain it. The following diagram is supposed to be commuted. May actually be a corollary of the way that geometric language is being proved, but I'm not sure about that. So on the one hand, I have this critical level FLE. Right? I can localize these guys to get modules on BunG, right? And here I can go to quasi-code locus G-Check by the following procedure. So remember, there was a correspondence, right, that mapped to both of these guys. It's the space of unramified global G-Check. Okay, so I pull push along that correspondence. So I realized I've used these letters multiple times, but that you overstar along that correspondence. Okay, and then this is supposed to sit inside the modules on BunG, right? Which is like, let's get this right. So it's you first apply that functor C, right, to go from quasi-code to encode no potency with support, and then do the inverse. So this is supposed to sit inside here. And this diagram is supposed to be, this is kind of one of the desiderata of like these global languages.
Why not take the bottom?
This is global. Oh, sorry, no. This is global systems, right? Which is supposed to be almost equivalent. There's the global overs, the global unramified overs are just like an intermediate here in the middle. But I'm about to explain what that is, so I'll come back in a moment. yeah, I hopefully it'll kind of make sense once I say the following. Okay. So this is supposed to commute. But independent of geometric line ones, we can prove the following unconditional. And this is a scooped up version of the theorem of Beilinson-Drinfeld. So what I've said so far tells me that I have a functor from quasi-co on the space of unramified local inverse. To P modules on BunG, right? Namely, I do this FLE inverse and then localize. Right? Go backwards and then localize. And the claim is that this factors through that space of unramified global inverse. Okay, so this maps the quasi-co unramified global overs by the functor Q over star. And this is supposed to factor through that. And this is what you would really call quantization of fixed analysis. It's some fancier version of poles, but if you kind of replace this with like really sorry, that shouldn't be losses, that should be overs, sorry. Yeah. If you replace this with like the global regular overs without poles, that's really what Beilinson-Drinfeld, something like this. And then we're cooking, right? Because now, if we believe, right, the conjecture I said earlier, which again is like mostly known, which is that if I have a G-check local system, I'm supposed to be able to lift it to a overstructure with poles, okay, especially if G-check is irreducible, right? And then I can consider the skyscraper sheet at that point, okay? And this is going to map to our. Okay. And again, this is kind of clear if you look at this diagram, what's going on, right? Because this will be like applying the functor P lower star to the skyscraper sheet will produce the skyscraper sheet at UChicago on the spectral side, okay? Whereas this functor is going to produce the corresponding D module on BunG, which remember is supposed to be the Hecke Eigensheaves. Okay, but in fact, you can show this unconditionally. This will produce a Hecke Eigensheaves with eigenvalue UChicago by tracing through, the fact that this was Hecke variant and everything else inside is. Okay, so that's what I wanted to say. We'll see. We'll see if we end up doing like the unramified version, obviously, or sorry, the kind of version with poles. It's great because it allows you to do it more or less for any Cuspidal Hecke this way. But there's definitely some technical simplifications if you don't allow poles and just consider the space where you have regular overs that are globally. And that's what Beilinson is. Okay, that's it. No, it's not too bad. The reference for this is Arabian game story, like the singular support. Yeah, singular support and the geometric line conjecture or something like this. Their original paper when they formulated it, I think. Yeah, it projects the BunG, so you just have to know that the image is quasi-compact and that the fibers are quasi.
This is BunG, but not X.
Yeah, right, but it's like, in particular, it projects the BunG, right, by forgetting the connection. And so you can study that map and use what we know about BunG to study Localization. And just, if you understand the space of connections on a given G bundle, you understand BunG, then you get full information. So I think I extracted most of this from the 2014 workshop in Jerusalem that's on Dennis's webpage. So like this, okay, yeah, that plus this particular statement is in Dennis's paper from the same year, proof of geometric geometry 2. He states this factorization. But lots of it seems to be like, you know, not written. Like this, for example.
I have a question, not directly related to the case. So I remember the geometric element. Every Cuspidal mobility module is always tempered and it's not like vanished as a weighted coefficient.
Yes.
But do you have a straightforward explanation for this fact?
Yeah, it kind of fits into this picture that I was explaining earlier. So like the tempered part of D-mod BunG is supposed to correspond to quasi-co.
But I don't.
So it's exactly this fact I said earlier that quasi-co on the irreducible local systems is the same as in-co notebook and single support.
But I don't expect such a result to be true in capacity, right?
I have no idea. Sorry. I mean, any hospital sheet is tempered. Yeah, I too ignorant to comment. Yeah.
Thank you.